Hi all. So today we will be discussing about cloudera Impala. So following are the topics that we are going to discuss today. So I'll go through like this the introduction contents of the topic. So first we will be discussing about introduction to Impala. So like what is Impala, how Impala comes into picture, and why Impala is attractive, and like why people are using Impala. Then second one we'll be discussing about why Impala is needed, because we have this powerful hadoop. Then why Impala is needed if we have the hadoop. Then third topic, like we will be discussing about the architecture of Impala, like how Impala is architectured, and what are the services of Impala, and how Impala works in a hadoop cluster, and all those things we will be discussing in the architecture part. After that, we will install Impala in a small Hadoop cluster, and we will see how to set up Impala in a Hadoop cluster. Then we will be discussing about a relationship between Impala and Hive. So that will come along with the architecture, but we will be discussing about the relation between Impala and Hive. After that, we will try practice some queries in Impala. So Impala queries will be executing in the cluster that we build. Then we'll be discussing about the authentication and authorization in Impala. So in a production environment, we need proper authentication and authorization mechanisms. Otherwise, the security will not be it will not be secure, and it will be vulnerable to and people can hack into it, and the data that we are storing and processing, it will not be safe. So we need proper authentication and authorization mechanisms for any framework. So we will be discussing about that part of Impala in authentication and authorization section. Then last part will be managing resources. So after installation of Impala, we need actually to manage the resources in a cluster. Sometimes every environment will be shared environment, so multiple people will be using this resources. So we need to manage the resources properly. Otherwise, a lot of we'll get into resource issues. We will chalk, the queries may chalk, and it will actually run into issues. To avoid that, we need proper resource management. So we'll be discussing about resource management also. So we can start with an introduction to Impala. So what is Impala? So Impala is actually an SQL engine, so that gives faster output. It's actually an SQL engine, so people can write queries and execute jobs, and finally we'll get results very fast using Impala. So why Impala is needed? Because we have Hive. So in Hadoop ecosystem we have Hive. So then why Impala is required? So we know, right, Hive executes. So what is Hive? So Hive is actually cell layer on top of MapReduce of Hadoop. So Hive is a layer on top of Hadoop. So this is uses HDFS and MapReduce. So Hive uses HDFS and MapReduce, and this is a query layer. So Hive is a query interface which uses HDFS and MapReduce. So the output of this Hive jobs will be it will execute Hive. All the Hive jobs will execute as MapReduce jobs, and the output the queries executes as batch jobs. So the output of the query will come after some time only, because it will not be near real time queries. So it will take some time, and the output of the MapReduce job will come as the Hive output. So Hive is not fast, but the advantage is Hive will work with large data. People don't have to write long MapReduce programs. People don't have to write long MapReduce programs. So this is actually another advantage. We'll actually take the advantages. We'll collect the advantages of Hive. first, then we will actually go to Impala. So hive will work with large data. People don't have to write long MapReduce programs. Then like people who know with SQL knowledge can easily write hive queries, because hive is also following the SQL standards, SQL 92. It's actually with SQL 92 standards. So hive also, people who knows SQL can very easily write hive queries. So people without programming, like people who don't have much knowledge Java can interact with map Hadoop. So the reason why hive became popular is like, instead of writing thousands of lines of MapReduce code, people can write few lines of queries, and finally like they can actually achieve the same results. The simplicity made actually hive very popular, like in the Hadoop ecosystem. For for achieving the same output using the Java MapReduce, people may like need good programming skills, and they have to write thousands of lines or hundreds of lines of program to get the real actual results. So that made actually hive very popular in this Hadoop ecosystem. And that is the reason, actually because of this reason only, like the people in Facebook developed this hive. So but later what happened was, if you are querying, so the previous all this RDBMS and all, so the queries are very fast, means with the limited data the queries are very fast and can process data, and it will give you the output very fast quickly. So if you want to get or publish the output of these queries to some dashboards or something, or if you want to even if actually the query is very simple, hive will take its own time and it will give you the batch, it will process in batch and it will give you the results. So that became actually a problem, because if you want to publish, if you want to show the end results quickly, it is not actually possible through hive. Hive will give you the output after some time only. So the thing is, hive uses batch processing. So that is actually the MapReduce. So hive is using actually the MapReduce backend, so it will be processed in batches only. So the output will be slow, query execution will be slower. So because of these reasons, actually people in Cloudera, they have developed a new engine which works on Hadoop called Impala. So people the main advantage of Impala is actually Impala also follows SQL standards, SQL queries. Impala also follows SQL queries. Impala works with Hadoop. Faster output, and so Impala provides very fast output compared to hive. Then it can work with hive. It can work with hive means people can work the same tables. So in hive we have the concept of tables, so all the data we will be accessing through databases and tables. So the same tables can be accessed from Impala also. We don't need any separate Impala cluster or something. So Impala will be using the hive's tables only. So whatever tables we have in hive, Impala also will use the same thing. So suppose I'll just draw a diagram like that. So suppose if we have hive here, so when we have tables A, B, C, we have 3 tables. So when we use Impala, we will be able to see the same tables. It's we will be able to see the same tables in Impala also. So means Impala is actually sharing hives metadata. So we will be able to see the same tables in Impala also. So we discussed Impala can access the hive table. So how will it happen? How Impala is accessing the hive tables? So I'll discuss before going into that. I'll just discuss actually a sample architecture of hive. So we have HDFS, we have HDFS, and on top of that, so this is the storage layer. And this is actually in case of Hadoop. So and on top of that we have yarn, so this is actually the processing engine, and on top of that, on top of yarn, we have multiple applications. So one is MapReduce, so another is Spark. So like that we have multiple applications on top of yarn. And on top of this, on top of the MR, so on top of the MR we can actually access using multiple ways. On top of MR we have multiple ways to interact. So one is through Java MR code, so another is through, we have several ways. I am just explaining 1 2 3, like 2-3 ways only. Another is through peak, another is through hive. So what these things are giving? So hive, so when talking about hive is actually executing, or it's using MapReduce, the Hadoop, entire Hadoop, and it gives us a query interface to the Hadoop. So when you check the Hadoop, you can see the files are stored just like a storage, where we store in a folder, like in a disk. So but when you access the same files using hive, we will get a tabular view. So when you access the same file, like when you access the data through hive, we will get a tabular view. So how this tabular view is happening? So hive achieves this tabular view by attaching a schema to the data. So hive attaches a schema to the data on top of the HDFS, and while querying or while viewing the data through hive, we will get the data along with through the schema. So we will get a valuable or structured feeling of the data. So suppose if we have a table, just like something like so suppose we have 3 columns. We have a table like, we will give ID, name, age. So when you look through hive, you will get a feeling like ID, name, age. So we will get a tabular feeling. But when you go to the HDFS and view the same data, you will not be able to see a tabular view. You will be able to see a simple file, simple flat file, or file in some other format. You will be able to see some file with some data, a file with some data. Suppose it will be something like 1 user 1 20. So this one user 120 became a table after attaching a schema to the data. So it means the hive table will be the data plus schema. So the complete thing, data plus schema, we got the hive table. So hive table is a combination of the data and the schema. So we know, right, the data is stored in HDFS. Let me save this. Data plus schema. So we know data is stored in, so hive table is data plus schema. So we know data is stored in HDFS. So where we store schema, where the hive is storing schema. So schema is stored in, like in the hive class and all, you might have discussed about hive metastore. So hive stores the schema in hive metastore. So hive metastore can be like, it's a small, it will be a small RDBMS table or something. So usually like people store, like people use MySQL, PostgreSQL, Oracle, etc. for storing hive schema. So hive stores the metadata in a hive metastore. So we will get the schema from the hive metastore. This is actually, we can actually like put this as hive. So suppose if you draw it in diagram, this will be the HDFS, and we have a metastore here, so here it can be like, suppose in our case it can be like, can be MySQL or Oracle or PostgreSQL, any database SQL. Yeah, fine. MySQL or Oracle or PostgreSQL. So when hive access this data, so we will put hive like here. When hive access data, people access data through hive. First it will check the schema, it will read from this metastore. It will read the schema from metastore and it will read the data from HDFS. Data. So whoever accessing hive, the data will be read from HDFS and the schema will be read from the metastore. So finally for the end user, he will get a combination of the schema plus the data. So he will get a structured data or valuable data, and all the process happens with the schema and the data. So Impala, what Impala does is actually, Impala shares the same metastore of hive. So we have like a number of tables in hive. So Impala, what Impala do is, Impala also access the same metastore of hive, and Impala uses the data present in HDFS. So Impala also uses the same metastore of hive, and it is uses the data present in HDFS. So then what will be the difference between Impala and hive? So like I said previously, like if people queries through hive, they will get results, like it will be slow, but if people queries through Impala, they will get faster output. So what can be the reason? So the reason behind this is hive actually uses MapReduce. So that is, it uses actually the processing engine of Hadoop. So it is like MapReduce. MapReduce for processing the data. But Impala uses Impala engine. We can call it as Impala engine. Later we will discuss like what is Impala engine. Impala engine. Impala query execution engine. You can call it like that. So it is not anything like Impala engine, but it is actually the Impala. Impala has its own engine for processing actually the data. So the data processing mechanism is different. So Impala also access HDFS, Hive also access HDFS. Impala also access the metastore, Hive also access the metastore. So since the data is same, the tables will be same, but the output of the queries will be like the speed of the output, speed of execution will be different, because Impala and Hive uses different execution engines. So Hive uses MapReduce and Impala uses a totally different execution engine for executing or processing the data. So now we will discuss like a little bit of Hadoop. So what are the daemons responsible for Hadoop, like for the execution of the entire Hadoop framework? So Hadoop has name node, secondary name node, then data node. So these daemons are responsible for the file system. Let's call, like we can separate the daemons of Hadoop, like these are responsible for the file system. So these daemons are responsible for file system, and we have yarn, like the MapReduce right now actually the yarn. So previously the previous generation of Hadoop, it was specific for MapReduce, so that was having only the MapReduce engine. So right now they developed Hadoop as a like generic framework. So the processing engine, they replaced the processing engine with a generic processing engine, so that like we can process, like we can use any applications to process the data on top of Hadoop. So we have yarn. So the responsible, like the daemons responsible for yarn are like, so it's a resource manager, so the block is small, so we'll make it a little big. So resource manager, then node manager. So we have two daemons, main daemons responsible for yarn. So like there are some other daemons also, but these are actually the major services responsible for, or like required for a Hadoop cluster. So these are the daemons required for yarn. So we have HDFS, yarn, and among this, so name node, secondary name node, data node. So data node runs, like if in case of a like Hadoop cluster, data node is the storage. So data node stores the data. Name node is actually the manager. We can call it as manager. So that manages the file system. So secondary name node, it is actually helping name node in checkpointing activity. So that actually anyway it's discussed in Hadoop section. So data node is actually the real storage daemon. So data node will store the data. Similarly, resource manager is the manager in case of the processing layer. So resource manager is the resource, like it manages the resources. Node manager is actually the worker. So node manager is the worker. So node manager is the worker, and it executes the MapReduce jobs or any applications. Similarly, data node is the storage. So data node, like in case of like I'll just draw a diagram of a multi-node Hadoop cluster, so then it will be more clear. So I'll just draw the diagram of a multi-node cluster. So this is master. Suppose we have master and we have one, like we have 3 slaves there. So here we have name node and resource manager. Source manager. So right now we can leave the secondary name node, so it's not a mandatory stuff. So here we have data node, and then node manager, here also we have data node manager. So this is actually like a representation of a multi-node Hadoop cluster. So data node is the storage, node manager processes it. Data node storage, node manager is the processing layer, actually engine, like process, it's a worker. So like data node and node manager are co-located, so like it avoids the transfer of data over network. So like we can achieve the processing of data in the place where it is stored. So node manager is actually part of yarn. So when you execute a MapReduce job, it gets executed inside node manager only. So like through node manager only it gets executed. So if like suppose if you submit something through hive also, it uses this daemons like name node, data node, node manager, resource manager. It uses this like entire Hadoop, like the name node, resource manager, data node, node manager daemons for the execution of the jobs. But in case of Impala, like as we discussed, Impala uses the HDFS and Impala engine. We can call it a Impala execution engine right now. So we'll discuss that in detail. So right now we can call it a Impala execution engine. So hive uses HDFS as well as MR, or we can call it as yarn. Hive uses HDFS. So yarn, like hive uses the HDFS and yarn. So if Impala is giving faster output, Impala will be using something else, right? So we discussed about I was talking about Impala execution engine. So Impala execution engine, it consists of like some daemons responsible for execution of the programs or queries. So along with the Impala is also a distributed, horizontally scalable, distributed execution engine. So Impala also has one daemon, like if you install Impala server, so Impala also has one daemon in every data nodes. So along with every data node, Impala also keeps one daemon of Impala, so that like the data will be processed in the same place where it exists. So in this way, the Impala's processing will be like, hive will be using data node and node manager for the processing, like for storage and processing. So Impala will be using the HDFS ka data node and the Impala server. So it will not be using node manager because it is not using, like right now we can like say like it is not using actually it's not using, we cannot say like it's not using yarn. I'll tell you actually how, like there is one point actually where Impala can utilize yarn, but Impala is not using MapReduce. So Impala is not using MapReduce, but Impala is using Impala server. So this is actually the basic architecture. So if you, so this is the basic architecture. So there are actually, like right now we can like start the architecture of the Impala. So Impala cluster. So Impala cluster, so Impala has mainly basically three daemons responsible for the entire operations. So one is actually Impala catalog service, one is Impala catalog service, another is Impala state store service, and Impala server. So these are the three daemons responsible for the operation of an Impala. So Impala catalog service and Impala state source. So the real execution, the real query execution happens like just before some time, like when I discussed about the Impala working of Impala, like I showed you Impala server. So the main execution happens, the query execution happens with Impala server. So Impala catalog service and Impala state store service are supporting Impala server with some useful operations. So Impala server is actually the query execution happens here in Impala server. So like Impala actually this is actually developed in 2012. The beta version of Impala got released in 2012. So at that time the catalog service was not there. Only the state store and Impala server were there actually. So two services were there. So I'll tell you actually like the working or the operations like performed by each of these daemons. So let me start with state store. So state store means, suppose if we have Impala server here in this node, in this node, in this node, everywhere. So when a user submits query, so Impala is actually not reporting to the Hadoop's processes, or Impala is not reporting to any other master daemon. So when you submit a query, so there should be some mechanism that tells that these are the daemons available for query execution. So without a master, how will it happen? Or without somebody to monitor like the status of individual machines or nodes, servers, so how will it happen? So Impala state store service is responsible for like checking the status of each Impala servers and relaying the status to all the Impala servers, so that like while executing the query, it can plan the Impala server can plan where it can execute the query properly, or where it can execute the query fragments. So before going into details of that, let me actually like tell you like how a query execution happens in Impala, or how actually the execution happens in Impala. So right now we just discussed the diagrammatic view, like how actually Impala daemons, like where Impala sits in a Hadoop cluster. So now what we have to discuss is actually the detailed architecture of Impala. So now we discussed Impala has Impala state store service. So this Impala state store service, it's also known as state stored, because it's storing the state of individual Impala servers and relaying it to the other machines. The other service is Impala catalog service, and the third one is Impala server. This is also known as Impala daemon. In short form, it is known as Impala D. This is actually the three services responsible for Impala. So from an end user's perspective, suppose an end user, this is the end user. So how he submits a query, because in case of Hive, we submits the query to Hive client and it will execute. So in case of Impala, how will it execute? So suppose this is a Hadoop cluster. So we have DN and we will put Impala server as IS. So again in this machine also we have DN and IS. Here also we have DN and IS. IS is for Impala server. So in case of Hadoop, we discussed like Hadoop is actually in master slave like architecture. So we have name node, and name node is the master and data nodes are the slaves for the file system. And similarly we have resource manager and node manager. Resource manager is the master of the yarn framework and node managers are the workers. But in case of Impala, it is not like actually a master slave architecture. It is again, it will work in master slave mode, but there is no single master. So each Impala server can act as a master. Server can act as a master. So this makes actually high availability very easy. So this is highly available. So if we have here in this cluster we have 3, like if you are considering the Impala, we have 3 Impala servers. So if you are saying like each Impala node can access the master, it means we have like high availability is there. There will not be any single point of failure. So it's like no failure. There is no single point of failure in case of Impala. So when a user submits a query, suppose this is the Impala server, a user can submit query to any of the, technically speaking, a user can submit query to any of the Impala server. So this user submitted the query to this Impala server. So this Impala server will act as the master for that query. So this Impala server, so the user, this is the end user, suppose this is the end user. So this user submitted query to this Impala server. So this acts as the master of this query. So we can call this like from the Impala times we will call as coordinator, query coordinator. So that node becomes the coordinator. So that node manages the entire operations of the query. So he will be the coordinator for that query and he will plan and he will actually distribute the queries to other nodes. So suppose like this node distributed the query to this, like the entire processing required for that query to these 2 nodes. So a small section got processed here. So suppose the entire query is q dash. So this will be processed like one part in q1 and q2. So the entire processing is q dash, and so some part will be processed here q1 q2. So one part of the query is got processed here, one part of the query got processed here. So this Impala server, so this Impala server is responsible for the process of this fragment, query fragment q1, and this Impala server is responsible for the processing of the query fragment q2. So these nodes acts as executor node. This node acts as executor. This is executor, not executor. So this the other Impala nodes where the query fragment execution happens acts as the query executor nodes. So here the first node acted as the master of the query, that is coordinator, and this second and the third node acted as the executor node. So after the execution, the results will be streamed back to the coordinator node, and finally the results will be published to the user. The end user will get the result from the coordinator node only. So the end user will get the results from coordinator node. So we have coordinator, executor. So an Impala server, so from this what we got to know, Impala server can act as a coordinator as well as executor. Any Impala server can act as a coordinator as well as the executor. So coordinator is actually the, like, that duty is for a query. So for a particular query, it can act as a coordinator and can act as an executor. So those are the roles. So suppose if we have three nodes 1, 2 and 3. So user submitted the query to first Impala server, this Impala server 1. So and it calculated and it planned the query, and it's planned like distributed to. So meanwhile, when it submits to this Impala server, it checks it communicates, the Impala server communicates with the name node also. It communicates with the name node, and it will find actually the file system details, like where the file is residing and where the blocks are residing and where to process. All those details it will grab from the name node. Then only actually it will decide where to process it. So depending upon that, it will send the request to the corresponding Impala servers. So like that it will process. So in that case, it decided like Impala server, this Impala server and this Impala server, like for the query, it like the remaining fragments should execute in this Impala server and this second and third Impala server. So but in the meantime, third Impala server went down. So what happens if the third Impala server goes down? Because Impala server 1 don't have any idea about third Impala server. If it is not having any idea about third Impala server, it will simply send the request for the processing. So the processing request will be sent from this one to this one. But when it reaches there, it fail because this is down. So if this occurs, the query fragment Q2 fails. So if this kind of situation occurs, the query will fail. So this is a problem. So for solving this problem, in Impala we have another daemon called state store. State store is a single process state store service. So we have state store service. So what state store service will do is, so communication happens between state store service and all the Impala daemons. So all the Impala daemons, so there is like all the Impala daemons, it has actually a service called like state store subscriber service. So it will actually communicate with state store, and the state store will have the details of all the Impala servers, whether it is healthy, whether it is up. All those details will be stored in the state store, and this will be relayed to all the Impala servers. So if this goes down, the third Impala server goes down, it means at the same time, if the third Impala server goes down, at the same time it gets the status and it will send the status to these two Impala servers and tells that like the third is down, so don't submit any queries to third one. So while planning the query itself, it will actually identify which all Impala servers are up and which all is down. So it identifies that. So thus in that way it will avoid the query failures. So state store service is very helpful in this process. So another thing is, state store is not a mandatory service for Impala. Impala server is, I told you, like Impala server is the daemon where the real execution happens. So for query execution, state store is not required. It is not having any role in query execution technically. But the thing is, if state store is not there, if it is offline, state store is not there, then like the Impala servers will not have any idea about the remaining Impala, like whether it is up or down. So up, like then in that case query failures may happen. So it will not be, the cluster will not be robust. So state store makes the cluster robust. State store makes the Impala cluster robust, so that like it avoids the query failures. Since like any Impala server can act as the master, high availability is already there. The only thing is when a like coordinator sends a query, like query fragmentation, like fragment execution request, that node should be available. So if that node is not available, the query may fail. So state store helps the Impala daemon to know the status of all the nodes, and it will update periodically. It will update the status of the cluster. So state store makes the Impala cluster robust. So that is the duty of state store. So state store makes the Impala cluster robust. So we'll discuss in detail about state store. So state store, it's like when you compare actually Hadoop cluster. So like for maintaining the the synchronization between distributed applications, we have a framework called Zookeeper. So for maintaining the synchronization between distributed applications, we have an application framework called Zookeeper. So similar, like state store also acts something similar to Zookeeper, because state store ensures the synchronization between these Impala servers. So state store mainly has three topics. One is Impala request queue topic, another is Impala membership topic, and another is Impala catalog topic. So Impala request queue topic, this is actually it contains the details of the waiting, like the queries waiting in the queues. So it contains the details about the queries in the queue. So all the Impala servers can subscribe to this topic. So in every Impala server, internally it will be having a subscriber service, state store subscriber service. So that subscriber service will subscribe to any of these topics in the state store. So as I discussed, so there will be a single state store. Only a single state store is required in a cluster. We can have a number of Impala servers, but only single state store is required in a cluster. We have multiple Impala servers. So this Impala servers will communicate with state store. So as I discussed, state store has different topics. So this is Impala server. This is another Impala server. This is state store. So the Impala servers will communicate with the state store. It will subscribe to any of the state store topics, these topics. So Impala membership topic, it actually contains the details about the attached and the detached nodes. So Impala membership topic, so when it subscribes to that topic, then the client, like whoever communicates with the state store, will get the details about the attached and the detached nodes. So another thing is Impala catalog topic. So if it is subscribing, if anyone subscribes to catalog topic, it will get the updates about the changes happen to the metadata. So these are the like main topics in state store. So state store actually, like it is just like state store service acts like Zookeeper. But it's not like it will not actually serve completely as a Zookeeper, but we can say it's like something like a Zookeeper. That is, so it is something like a Zookeeper in Impala cluster. So it's something like a Zookeeper in Impala cluster, which helps in nice synchronization. Impala servers. So this is actually the main working of a state store. So state store is it is a very lightweight service, so it can be placed in any of the nodes. So it is present it will be installed in only one node, and Impala servers we will install in all the data nodes. So this is actually the basic overview of Impala state store service. The third service in Impala is Impala catalog service. So the third service in Impala is the Impala catalog service. So we discussed about Impala server, Impala state store. So initially, when Cloudera developed Impala, so in 2012, this catalog service was not there. So initially, in the beginning we discussed that. Impala, it uses Hive's metastore for storing the metadata. So Impala uses Hive's metastore for storing the metadata, and it uses SDFS for storing the data. Storing the data. So Impala caches the metadata in memory. So Impala is actually it is a framework with it is an in-memory processing framework. Impala is an in-memory framework. So Impala process data in memory. So the processing will be very fast. So it's an in-memory processing. So Impala caches data in memory. So it will first read the metadata from the metastore, and it caches the metadata in memory. So any recent changes, any modifications happen to the metadata, happened to the store, should be updated in the in-memory copy. So this is a requirement. Any modification happen to because if it is holding in memory, so we have actually a physical metastore also. So if anything changes here, we need the same changes to be reflected here also in the Impala server also. So that thing we have to achieve. So since it is caching everything in the metadata in memory, all the modifications happen to the metastore should be updated to the memory copy, in-memory copy also. So in the previous version, in the earlier versions of Impala, you can observe if you create any table, in the initial versions of Impala, the create table was not there actually. But at that time actually, if you modify the table content, anything, so you have to do a refresh or invalidate metadata. So I told you the modifications happening to the metastore. So this can happen either through Hive or Impala, because suppose in the current state I have tables tab 1, tab 2, tab 3, and one user is actually using Impala, one user is using user 1, and another is using Hive. So I'll put Hive also here. So another user is using Hive. So user 2. So both are simultaneously using Impala and Hive. So in this time actually, user 2 created a table called tab 4. User 2 created a table called tab 4, and user 1 he created a table tab 5.
So user 1 created tab 5. So this means actually two metadata updations happened actually. So when we create a table, the updation happens directly to the meta store, physical store. So tab 4 and tab 5. So tab 5, the table 5 got created from Impala itself, and table 4 got created from Hive. So within Impala, whatever changes happens, within Impala, whatever metadata modification happens, so the catalog daemon refreshes the copy, it actually refreshes the metadata. So if tab 5 is created, it means like the tab 5 is created, it happened from Impala. Tab 4 actually it happened through Hive. So tab 4 still actually right now also, this is actually a problem with Impala. We have to trigger refresh or invalidate metadata. But in previous versions of Impala, we have to do the refresh or invalidate metadata for tab 5 also, because at that time the Impala will not refresh automatically. So now they introduce the catalog service. Catalog service will do the refresh for all the operations. So catalog service, this will do the refresh of metadata for all the operations happening through Impala, not Hive actually. So now also we have the problem like using Hive. If you may do any changes, we have to trigger invalidate metadata. But catalog service, this will, so I'll highlight this. So the catalog service will do the refresh of metadata for all the operations. This metadata means in-memory copy of metadata for all the operations happened through Impala. So it will be up to date with Impala stuffs. But if any creations or modification happens through Hive, then we have to trigger invalidate metadata. So invalidate metadata is required for, so if any changes happened in the metastore because of Hive actually, through Hive we created table 1, table 2. So though like table 6, table 7, all those things actually, for getting the effect in Impala, we need invalidate metadata. For reflecting the operations happened in Hive, we still need invalidate metadata. So I will put it in a clean sheet so that like everyone will be clear about this topic. 6. So clear sheet, I will put catalog service updates all the Hive. But happened through, not through Hive, it through Impala. So no the invalidate metadata is a command for refreshing the in-memory copy of metadata. Invalidate metadata or refresh. Refresh was actually a previous command. Impala. But we still need to use invalidate metadata command for reflecting changes happened in happened through hive in Impala. So Impala still needs the invalid metadata command for reflecting the changes happened through hive in Impala. So invalid metadata is required. Now also we have to use invalid metadata for, like, if something happens, some operations happens through hive, for reflecting the changes in Impala, we still need to trigger the invalid metadata command. But if any operation happens through invalid, through Impala, those changes will be automatically updated. Though this catalog service is actually responsible for this operation. Catalog service is responsible for this operation. So like when Impala released for the first, like when in the initial beta versions of Impala, catalog service was not there. So at that time, actually for every operations we have to use this invalid metadata or refresh command. After every operations, at that time we have to use this invalid metadata or refresh command. Right now we need only for the hive operations. Like whatever changes happen through hive, we have to use invalid metadata. That is the advantage of catalog service. So now we discussed about like the Impala server, catalog service, and Impala state store. So again, catalog service is a single process. It is a lightweight process. So catalog service, like, it is a lightweight process. Catalog service is a lightweight process. It is a single process. Like we don't need n number of catalog services. We need only one catalog service daemon running in a cluster, running for an Impala, like entire Hadoop cluster. So we need only one process, and like usually actually we run catalog service. We use same node for catalog service and state store. So like it can coordinate each other. So like we usually use the same node for catalog service and state store actually. Like both of them are actually state store service. So state store service is also known as state stored. So we use the same node for catalog service and state store. So now we discussed about the three main daemons responsible for Impala. So now we can put everything together actually in a diagram. So now we have actually a full idea about an Impala cluster. So we'll put Impala server, and we have data node, we have name node, then like we can put a small machine where we'll put the catalog service and D and catalog service and state store service we'll put in a small machine. So in this way we have our Impala cluster ready. So So the Impala state store catalog, this communication happens between every machine, and like the name node communication also happens actually. So this is actually a basic architecture of Impala actually. So a colorful architecture I will show you. So you can see this is actually like this is actually an Impala cluster. Suppose like this is the HDFS, we have cloudera Impala on top of that, HDFS and HBase, we have HDFS and HBase cloudera Impala. So here like people are accessing, here we have the hive metastore. So this image I have taken from cloudera website. So this is actually the hive metastore. So Impala access the cloud hive metastore, and communication happens between Impala daemons also, and people access through Impala shell, Hue, JDBC, ODBC client. These things we will discuss later actually. Now we will discuss this. So just like have a quick view of this architecture. Impala HDFS. So HDFS actually like the data node and the name node combination. That is the thing. So and every Impala server is accessing the hive metastore. This is actually a basic view of Impala cluster. 3 ways to access Impala. Fine. So now we have a basic idea, like we have an idea about the Impala cluster. So the next thing is how people can access this Impala. So in case of hive, we know we can like hive can be accessed using through several ways. One is actually through hive has hive CLI. There is, if you type hive CLI, hive has on hive CLI. Now hive CLI is deprecated, so we have a new hive command line called beeline command line. So third option is actually we have Hue web UI, Hue interface. Using Hue we can access hive. Then fourth option is actually using programmatic way, JDBC ODBC connection, BC connection, you can access hive. And fifth way, so this is actually JDBC ODBC connection, it's a broad category, so it can be through Java programs, Java or any other language, Python, Java, or basically through multiple programs or applications through this JDBC ODBC interface. So applications means like we can connect Excel, our Microsoft Excel to Hive. There are like ODBC connectors to connect to Hive. So we can connect Tableau to Hive, we can connect Pentaho, like lot of things. All these tools actually we can connect to Hive actually. So all these like connections happens through JDBC ODBC interface. So similarly, Impala also we can access in several ways. So Impala, same as hive, we have a very good shell, Impala shell. We can call it as Impala CLI or Impala shell. Impala shell. We have Impala command line for accessing Impala. Then if you want to access, we have actually another interface. The Hue also has Impala. Then third option we have again JDBC ODBC interface. Using this we can connect like Excel, or we can connect Tableau, we can connect Pentaho, we can connect all these like open like Spotfire, all these like tools we can connect to Impala using this JDBC ODBC or Java programs. If you want to query Impala, trigger the queries using Java programs, we can use JDBC ODBC connectors. Like Python programs we can use, like all these connections actually happens through this JDBC ODBC interface. So that is with Impala. So we'll be discussing like now we got a brief like like a picture of Impala, like this is the way Impala this is the architecture of Impala, and we can access Impala using several ways. So we can access Impala using several ways. So with this actually I think we got a brief idea about Impala. So and next thing is actually like we'll try to install Impala in a small cluster. so that like you will know, like you can easily install, you can easily follow the procedures, like the follow the steps, and you can also install Impala. So that is, and since Impala, like one more thing, so since Impala is actually like utilizing like processing everything in memory, it needs, the memory requirement for Impala is high. The memory requirement compared to MapReduce MR, the memory requirement for Impala is high. High. So Impala, like if you want to install Impala in a cluster, you need actually like nodes with more memory, a physical RAM, for better performance. Otherwise actually the query may fail, or the queries will be slower actually. So the memory requirement for Impala is high actually. So we'll install actually a small Impala cluster, then we will see actually how to do this.
So I'm going to show you how to install Impala on a single node. So like you can follow the steps and you can copy the, like you can also do the same step like setup. So like Impala the Impala VM provided by Cloudera, it requires like 6 GB, minimum 6 GB RAM. So like if your laptop is not having enough configuration, you can actually like launch a small EC2 machine with some enough configurations, or any other from any other cloud service providers, and you can install Impala there. So I am actually using Amazon EC2 machine for installing Impala. So I logged into, like I am actually attaching a document how to launch an EC2 machine. So I am right now actually I am inside the EC2 machine. This is actually putty. So using putty I logged into the like EC2 machine, and now I am in the EC2 machine. So this is the command line. So I made it actually in the white screen, that's why you are seeing it in the white screen. So this is the Cloudera documentation for installation of Hadoop. So first we will install Hadoop. So we will install the Hadoop quickly. So here once you like go through the documentation, so there is a step like add CDH5 repository. So I am going to use CDH5. So my operating system is actually CentOS 6. So CentOS 6. So I am going to add actually the repository of CentOS 6. So this is the repository repo file. So this is the repository. So this is the URL. It contains actually all the installables of CDH5, and this is actually the repo key also. So I am going to add this to my machine, newly launched machine. So this should be added in the location /etc/em.repos.d. So in this location we have to add. So I am adding cdh.repo. So I am just creating a file called cd. So before that I will show I am in this location /etc/em.repos.d. I am creating a file cds.repo, and I am pasting the contents. Whatever I copied from there, I am pasting it here. So now I have a repo file here. So this is the newly created repo file. So now I am going to clear the yum cache. I am clearing the screen. So the command is yum clean all. So this is the command to clean the repo cache, yum cache. Now I am going to install Hadoop. Yum install. First I am going to install name node Hadoop. So before installing everything, you have to check whether Java is available or not. Java version, Java is available. JPS is not there actually. So like ideally Sun JDK, Oracle JDK is required. So we have Open JDK. So Hadoop works with Open JDK also. But like since this is a trial and training environment, we can continue with Open JDK right now. So JPS is not there. So I'll install. We have to install the Open JDK devel package. Open. First we will see actually the package name. So in info JDK star. We'll put this. We'll see the package name. I just So lot of packages related to JDK are there, and m info means it will list all the packages that are related to that name. So I need actually a JDK devel package. So currently we have OpenJDK 1.7. So I need actually this one, Java 1.70 OpenJDK development devel package. So the command I triggered was minfo star JDK star. So it will list all the packages with that keyword. So see here, actually you can see Java 1.70, it is installed. So I need the devel package so that the JPS will be there. So Impala, like this one Java 1.6.0, it is not required. So 1.6.0 not required. I need the 1.7.0 devel package here. So 1.7.0 devel, it's not installed. I am going to install this devel package. So yum install, the command to install is yum install devel package. So this will download. So this will download from a remote repository. This will download the RPM, the installable corresponding to this Java from a remote repository, and it will install it in this Linux machine. So I'm installing this package. So this got installed. Now when I type JPS, JPS is there. So JPS will list all the Java running Java process in this machine. So it will help us actually to identify the process is running or not. It is very useful like package actually. So I'm installing name node. So since we added Hadoop repo, cloudera repo, we will be able to do yum install Hadoop HDFS name node. So these installation steps, it's everything actually it is properly mentioned in Cloudera installation documentation. So this is the documentation. It's clearly mentioned here. I am just following the steps only. So since Hadoop is actually like we just need Hadoop, so that's why I am installing Hadoop. On top of that only we can install Impala. So first we install name node. It's asking for the confirmation. It's installing it's updating lot of packages, it's installing lot of packages. So this speed depends on the internet connection. Since I am using the EC2 machine, the internet speed is very high. So that is the reason actually this is getting installed very fast. You can do the same installation steps in your local lab. If you have a Linux laptop or desktop, you can do the same steps. Only thing is you need an internet connection. So here you can see the packages are getting downloaded and installed very fast. So the size is actually like this size, like it will be some 500-600 MB, but it got downloaded and installed very fast. So now I have HDFS ready, HDFS name node. Next service is data node. So data node also got installed. So now I have HDFS, the basic service, the name node and data node. So the configurations related to Hadoop, it will be located in /etc Hadoop conf. So here we have the HDFS site.xml, core site.xml, mapred site.xml, and yarn site.xml. So we have to do we have to configure this. So for proceeding further, we have to configure this. So I'll just, so I have a set of configuration, like we have to write the fill the configurations. So I have some handy configurations with me. I'll share the configurations with you. So in HDFS like core site.xml, I am going to put this value. So HDFS master 8020. So this is the name node URI. So master is actually right now unknown. So what we will do is I will add this entry in the etc host. So right now I just need IP address of this. So this is the IP address of this machine. I am just putting this value in etc host. So that like, so this file I am putting this IP address master. So now when I ping master. So this is a known host because it is like we are creating an alias for this node, this master to this node actually, so that wherever I put the master, it will consider this machine as the node. So course.xml, we added the entry configuration, we put fs dot default fs, we put this entry. Then next thing we will do is we will put hdfs site.xml. By default actually some configurations are there, I'll remove that. So I'll remove the entry there. From there, yeah, I'm going to put my entries. So I'm putting so these are the entries required for HDFS. I'll share this configuration with you so you can also do the same thing. So the one mandatory thing is like I'm putting these remaining configurations to the HDFS site.xml. So since we have only one node, I'm putting the replication factor as 1. Let me see. I think the session got expired. The section got expired. Site.xml. So I'm removing the existing contents. I'm pasting the new contents. So here I'm putting like the replication factor 1 and one necessary thing for Impala. So one is the short circuit read we have to enable for Impala. I will explain why it is needed. So short circuit read we have to enable for Impala, and these are the basic configurations where to store this like HDFS, like name node data, where to store the data node data, all those things. So name, then HDFS we have to enable this block metadata enabled. This how we have to enable this for Impala. This is actually this configuration DFS data node DAR. This is for like storing the where to store the data node storage. So these are the basic configs. So now we have yarn site.xml. So now we have core site.xml ready, HDFS site.xml ready, and now we are going to edit yarn site.xml. Yarn site.xml. Right now it is some values are there. I'm going to put. So this is fine. Seems this is fine. Nothing is required. This will be fine for the basic yarn setup. No, then maprod site.xml, we will see what is there. Maprod we have to put some values. So we have to specify what is the framework and all what. So what this is a main important property for yarn, maprod.framework.name. If it is yarn, it will run in the yarn mode. So we put, then this is actually the history directory and like the staging directory we are mentioning here. So these are actually the basic configs, nothing extra. So Hadoop installation, I'm just rushing it through the Hadoop, like I'm just going fast through the Hadoop installation steps because we already did all these steps in your like previous classes. So that's why this is actually not that much relevant. So we just need a Hadoop cluster app. So now I am doing, I have to format the name node. I'm clearing the screen. So first thing is, now I have all the configurations ready. So I have to format the name node. I have to format it using HDFS user. Hadoop name node. So format, it should be hyphen format. It's not like that, so I didn't put actually hyphen format. Hadoop name node hyphen format. This will format the name node. So this formatted the name node. Format means it will clear the directories and it will create the name node directory structure. So now I'll try to start the name node. init.d hadoop hdfs name node start. If everything is fine, it should start. So I'm just checking the logs. .log. We'll figure out whether if anything went wrong. Okay, so things are fine. It seems things are fine. So we'll just check the status also. Status name node is running, so we can proceed with the next step. So next thing is we'll start the data node /etc init.d hadoop hdfs data node start. So what happened? Failed to start data node. So we will see the error log. So showing shutting down data node tail -100. So it is showing where runs sockets. Okay, so we'll uncomment that property. So we added this property in hdfsi.xml. That directory should be there. Okay. Anyway, it's not actually it's not required. It will let it run in the default. I uncommented that property dn sockets, and again I am trying to start data node. Yes, so we'll see the log. So data node logs are fine. Then we'll see the name node log also. So we can see, yeah, this data node got registered to the name node. Adding new node to default track. So it means the data node got registered to the name node. So name node and data node are working fine. hadoop-ls. So the super user for the file system is hdfs. So that you know, I think, because that is discussed in the Hadoop sessions. mkdir will create /user socket path. 1 minute, it needs the socket path, it seems. No such follow directory. Hadoop hdfs name node.pid. mkdir-p will create the directory first. We'll make it to HDFS owner. We'll try to restart the data node. Because this was showing an exception, so there is a reason we are trying to create this, because it is mandatory for again error is coming. This directory is required for, like, once you enable short circuit, this directory is required. So like you have to create this directory first. This is a file, so don't create this file. So you have to create this directory first and give ownership to HDFS user. So that is the solution for that problem. So it will be something like the command I am just putting it here. It will be mkdir-p this directory sockets ch on HDFS this directory, then start the data node. So that is the resolution for that. Anyway, we have the like data node up, hadoop data node status. Okay, it's up. So now we will create. So HDFS is a super user, so I'm creating a base directory using that /user/ creating a directory first. So I'm creating another directory ec2-user, creating directory for ec2 user, and I'm giving ownership to ec2 user -user to the directory, so that like ec2 user can access the contents inside the directory. Now the file system is up. Then I'm just starting not HDFS. Okay, so I have to install yarn services. Install hadoop yarn resource manager. I'm installing hadoop yarn resource manager. Then I have to install node manager. Installing node manager. Then I'm installing yarn hadoop use history server. I'm installing history server. And then I have to install yarn proxy server. This is not required actually, let it be there. Proxy server also installed. So I installed. So these are the daemons I installed right until now. Resource manager, node manager, job server. This proxy server is not required. Job history server is also optional, so we can proceed with the remaining thing. So we'll try to start that service. .d hadoop yarn resource manager. So we'll install hadoop MapReduce package also. We have to install hadoop MapReduce, hadoop client packages also, client client. So client got installed. Yeah, okay. So all the services are installed. Now we'll start. So the Hadoop installation steps, it's properly mentioned in Cloudera documentation. You can follow that. I'm just going through the steps very fast. So Hadoop yarn source manager, starting the resource manager. Just checking the logs of resource manager, seems yeah it's up. Then we are starting the node manager. Yeah, node manager. So node manager also will check the status. It's up, it's running. So seems Hadoop cluster is up. Now we need a MySQL instance because we need to install Hive. I'm installing MySQL server. So MySQL is installed. I'm starting MySQL instance. init.d MySQL d start. So MySQL started. So the command is init.d MySQL d start. So MySQL d started. Then we have to install Hive. Install Hive. So Hive JDBC Sentry, everything will be installed. Hive. The Hive 1.1.0 version is getting installed. Now down this version because we have to apply the schema for this version. It's getting installed. Yeah, it got installed. Then Hive server 2 we have to install, and Hive Metastore also we have to install. I'm installing both the services together, Hive server 2 and Hive Metastore. So both the things is installed. So now we have MySQL running MySQL server also. So we are going to use Hive like MySQL as the Metastore for Hive. So we have to configure that. So we need MySQL connector also. So this is actually, yeah, we can install the connector Java using install MySQL connector Java. So because the Hive needs to communicate to the MySQL, so it needs actually the JDBC connector. So MySQL connector Java connector is required for that. So we installed that using MySQL. Install MySQL connector Java. So it's installed. Now I'm just logging into MySQL. I'm creating a database. Create database. Hive user Hive these are basic steps. Grant all on hive.star to percentage. So Hive user can access this database from any of the nodes. We will try to log in through Hive. MySQL -u Hive -p. Access denied. So some problem is there. Again we have to go there. So grant all on hive.star to hive@master also will put. Master will put localhost also. So now we are able to log in. So now we have to apply the schema of Hive 1.1.0 to this Hive. So we already installed this Hive. So user lib Hive. So we have scripts folder here. cd scripts. Then we have Metastore. Then we have upgrade. Then we have MySQL. So we are using MySQL database, that's why. So here we will be having, I'm sorry, yeah, this is the schema. So we need this schema to be uploaded to mysql hyphen u hive hyphen p at 123, and I am doing source. So right now I am in this location, this place where the schema exists. I'm just putting source that file .sql. So this will create all the schema. So I have to use the database also. Show databases, use hive. So I am applying this in hive only. So source, so all this right now, if I type show tables, I can see lot of schema tables got created inside that MySQL Metastore database. So now our MySQL is ready. Next thing is we have to configure the hive.xml. Conf, we have hive.xml here. So we will be having some default values. We have to replace it with the actual values. So I have the configurations ready with me. I will share the configurations later. So I have that values with me. So I have that values with me. So I'm just replacing those values. I will share the configs with you. So I'm removing these values. I'm putting my values. So I'll just explain what I put. I just, instead of the Derby data, default Derby database, I used, oh, it's this one. Our database name is Hive. So I'm putting Hive, that is the database. This is actually the database connection URL, and I put, previously it was Derby driver. So I put MySQL connection driver. Then this is the username of MySQL database. This is the password for MySQL database. I'm just, so our database password is hive@123. hive@123. Data auto create schema. We already created schema, so we don't have to create automatically. I put it false. Fixed data store, we have to enable true. Then we have the Metastore running on the, so this one we have only one machine. We have to put master. So we have the Metastore running in master colon 9. So by default the Metastore runs on 9083 port. So it will be running on, so this will be the Metastore URI thrift. So Hive Metastore server will be running on this port. So impersonation enabled true, because like if I enable true, then like user identity will be enabled actually, because if I like, if user 1 executes a query, then it executes as user 1. So that is Hive impersonation. Like any user executes a query, that user will, the query will be submitted in that user's name. So now we will start the Hive services. First we will start Hive Metastore. Hive Metastore server start. Before that we will check whether the MySQL connector jar is present. Ideally it should come in where hive lib hive. So we'll check user lib hive lib. So we need MySQL connector jar / name. Previously we installed the MySQL connector, so that will be present in some location in the machine. Yeah, it is present in this location. So we just have to move this jar to this where lib hive, or like this location. So because otherwise the Metastore won't start. So we have to, because previously I installed yum install MySQL connector Java, so that installed this jar actually. So we have to copy this jar to /usr lib hive lib. You have to copy it to this location. So now it will work. So previously I started the Metastore server. I will just check the status of the Metastore server. It is running. So Metastore server is running. We will just restart the Metastore server, because it Metastore restart because the jar was not present initially. So hive server 2 also we are starting. Now we will, I'm just taking a duplicate session of this. I'm just logging in as EC2 user. We'll just see, we'll just try hive. So what is this, what error is this? So yeah, it needs a temp directory. That directory is not there. So, and it needs a metastore directory also. So we have to create the warehouse directory first. So hadoop -u hdfs hadoop fs -mkdir /user /mkdir -p /user /hive /warehouse. Warehouse directory, I'm just giving hadoop fsch mode 777 to this directory. To user hive directory. Now when I try from ideally it should work. One temp directory also I have to create. Again permission, yeah, I have to create a temp directory also. So fsmkdir /temp I have to create. Then I have to give permission to temp because it stores the temporary directories files there. Then now we will see hive whether it works or not. Now it's coming. Yeah, show tables, it will be empty because it's a fresh cluster. We are creating a table. Test1 id int. Yeah, it got created. Show tables. Yeah, our cluster is up, hive is up. Now next thing that we are going to install is Impala. So right now the prerequisite for Impala is ready. So now we can install Impala. So yum install. So prerequisite is a Hadoop cluster with hive. So now we can install Impala. So first we will install Impala -server. So Impala is also like present along, it's also, it will come with CDH, it's coming with CDH5. So we can install very easily, like the same repo will work. Yum install Impala server. So we'll install Impala server. So it's installing some dependent packages also. It's installing the base package Impala, then it's installing a base library for HBase, and Hadoop lib HDFS also it's installing. So it's yeah, so it got installed. Then Impala state store, we'll install Impala state store. It's stored. We'll see info star. So we have Impala state -store. Yeah, so it is yum install Impala state -store, Impala state -store. So Impala state store got installed. Then next thing is Impala catalog server. So again, yeah, Impala catalog. So that daemon also got installed. Now here we have all the Impala daemons. So the next thing is we have to copy the core.xml, hdfs.xml and hive.xml to the Impala conf directory. So we have /etc/impala conf So we have to copy the hive site.xml. So currently this is the location, so we have to copy ln. So I'm, instead of copying, I'm just creating a symlink -s / etc hadoop conf / core site.xml .xml. I'm creating a symlink so that like only one file will be there, but it will be linked to this location also. So now you can see core.xml came, but the actual file exists in this location. Similarly, I am creating symlink for hdfs xml, hdfs site.xml. So hdfs site.xml also done. Now we have to copy, similarly we have to copy hive site.xml, hives conf hive site.xml, then /etc impala conf hive site.xml. Now we have all the three things here. Now one more service we forgot to install is Impala shell. Install Impala shell, otherwise we will not be able to access from command line. So Impala shell we are installing. Yeah, Impala shell done. So we'll start Impala state store. Will start starting state store. It's running. So I'm just starting catalog server, catalog start. Catalog is also running. Then Impala server start. Impala server is also running. Now we will try to go to the log into the Impala shell. So from the EC2 user I am trying. So clear. So we already created a test1 table in hive, so we will see whether it comes in Impala or not. Shell. So see, yeah, if it is connected it will show like this. So we have the host name like master, so it's connected because it's connected to the Impala daemon. That is the reason it is showing like master colon 21,000. If it is not connected, it will show something like not connected. I am disconnecting it. We'll see. So disconnect is not there, but yeah. So I can connect in another way also, using connect command also. So if I log into Impala shell, I can connect to any of the Impala daemon using connect command, either using connect command or else while logging in with the shell I can directly use -i option, Impala -shell -i master. This will also connects me to the master. So this will be the command line for Impala and show tables. So it's showing the test1. So we have the test1 created. So this one we created using hive, not through Impala. So it is here actually. So I'm just creating another table here, test2 string. I created here through here. I'm creating through Impala. So test2 I created here. Then I'm trying to, now I'm exiting from Impala shell. So now I'm trying to log in using hive. So ideally 2 tables should come. So here we can see test1 and test2. So 2 tables got created. So from this we understood that like the tables created in Impala are visible in hive, and tables created in hive are visible in Impala. Tables created in hive are visible in Impala. Then we will actually like create some, yeah, I am creating a sample data set. like we can create some sample data set, test data dot txt, one ram 25 28, two varun 23 25, four 30. So these are like id, name and age. Suppose we have 3 records. I am putting it to hdfs. I have some kdr slash, I'm putting input a directory called I'm just uploading it, that is fine. So put test.txt to slash user slash ec2 hyphen user slash, I'm just putting into hdfs 7ls. So user ec2 user test data is there in hdfs right now. So now we will create a table in hive. Table user underscore data id int name string age int row format ted fields terminated by comma. So the table got created. Then load data in path. I'm just copying this data, taking this data, load data in path. I'm loading the data to the table. Load data in path into table. The table name is user data, user underscore data. So star from user data. So I'm getting the data. Now I'm trying to this job actually doesn't trigger any MapReduce job. So I'm trying to trigger a MapReduce job using, like I'm trying to find the count of users. I can put count of star from user data. This will ideally trigger a MapReduce job.
Now we can query the test data from user data. We'll run a MapReduce job. So it's taking like map phase, map 0, reduce 0, map 100, reduce 100. So totally it took like 20.197 seconds for completing this query. So like 4 rows, it took 20.197 197 seconds. So we will try the same thing here using Impala. Impala shell. We have the Impala shell. So I have a database called testing. So I have to invalidate metadata because I created the database using hive. I have used testing. It's working. Show tables. Yeah, user data is there. Select count of star from user data. It gave me output in 4 seconds. See, when I queried for the first time, it gave me the output in 4 seconds. but when I queried for the second time, it gave me output in 0.47 seconds. So it means like the first time it is like caching something, it is actually reading the data. So once it reads, actually next time onwards the query performance will be much better. So the first query actually executed in 4.12 seconds, which is far much better than Hive. It took actually 20 point some second 20 plus seconds for querying this, for executing the same query, but Impala took only 4.12 seconds in first step. So that is like one like in the initial step, and it took only 0.47 seconds in the second step on the subsequent execution. So this means Impala is very fast. Select ID from user data. Again it gave me output in 0.35 seconds. So Impala is much faster. So if I trigger the same query in Hive, we'll see how long it will take. If I query the same query in Hive, so this is actually 0.49 seconds because it got cached actually, that is the reason. I'm just triggering a dummy query in Hive just to trigger a MapReduce job. So just select count of ID from user data, group by ID. If I trigger the same query from Impala, it took only 49 seconds, same query. So this is actually the performance difference between Hive and Impala. But there are some advantages for Hive and there are some advantages for Impala. Like Hive actually, like the only what it guarantees is that like whatever memory, like even in case of small machines, like whatever, like even if actually the memory is not that much high, it can process any size data. Only thing is it will be slow. It will process in batch. It will be processing in batch way, but it will give you the output for sure. But the problem with Impala is like if it is not meeting the memory requirement, the job will simply fail. So in case of Hive, suppose if your machine is like not that much which is not having very huge memory and all, but if you have actually the memory enough for like configuring the like required heap sizes for map slots, reduce loads, node manager, all those things, then that in that cluster actually the Hive, the MapReduce jobs will execute properly. But the memory requirement for Impala is very huge, because if the map if like any like from my experience, like any job, any MapReduce job of like with any sized data can be executed in a node which is having like somewhere around 20 GB memory. 20 G, if a node is having 20 GB memory, like individual nodes are having 20 GB memory, that is enough for actually executing MapReduce jobs with any huge data and any complex logics. Only thing is it may be slow, it can be slow actually. But in case of Impala, if you have a 20 GB node machine per node, 20 GB RAM per node machine, per node cluster. So suppose if you have 5 nodes, each node with 20 GB RAM, so like you will not be able to execute huge queries in that cluster, Impala queries, because in the initial stage itself, Impala will check for the memory, per node memory requirement. So if that per node memory requirement is not meeting, the query will fail. For huge queries and all, the per node memory requirement will be something like 80 GB, 70 GB, like that. It will be in that way. So Cloudera's recommendation for Impala capacity planning, so they are mentioning like 128 GB machine per node, like each node should be of 128 GB RAM and all. So means for huge queries, for executing huge queries and all, means but that is actually the memory requirement for Impala cluster. But for MR MapReduce we don't need that much memory. So that is like for if our requirement is actually batch processing, like if you don't want output very quickly, then hive is actually best. You will get actually output even if it's low. You will definitely get the output. The queries will not fail. Impala, the problem is if you are not controlling it properly. So if you are not giving the proper memory allocation, the jobs may fail. So that problem is there. The main advantage is like the end and the like with like if you know actually like the memory requirements are proper, then with that memory configurations, like the set of queries, those queries will execute very faster compared to hive. It'll be like sometimes it will be like 100 times faster, sometimes it will be like 50 times faster. It totally depends on the type of query, but it will be faster. So that is the advantage of Impala, and that is the advantage of like that is the main difference between Impala and hive.
So just like hive, in Impala also we have the concepts of like manager and external table. So manager table, like right, I think you already have like the hive knowledge. So manager table means like when you drop the table, the data associated with the table also will get deleted. So if you drop a table, the table as well as the data associated with the table, both the things will get deleted. But in case of an external table, you will be pointing your table to an external location. So you are like you have, so in case of there are like you can have managed table and external table. So manager table, the like once you drop it, drop means once you drop the table, data plus the schema. External table means we are pointing the table to a different data location. So once you drop the table, it will delete the only, it deletes the schema only. This is actually the same as hive only. So here we can actually try to create a manager table first. So manager table also we can specify the location. So I'm specifying the location sample1. Okay, because Impala user is executing this query, that is the reason. Impala user, so this query, like it is executed. Impala is actually internally running the queries as Impala user. So Impala executed this query, so we need write access to this location. That is the reason it failed. So if I give write access, it will succeed. I'll just exit. So we'll actually I'll create a separate location then, because it is not a good practice to give all permission to all permission to this directory. Otherwise I'll set FSCL. So we can give like we can check the groups. So groups, then username will give Impala is a user actually. So we found actually like that Impala user is not having right access to a particular directory. So we will see the groups associated with the Impala user. Impala. So Impala is part of hive user. So yeah, so hive group. So these are the other groups that I created actually. Anyway, like Impala is part of hive group. So basically Impala will be part of hive group. Hive is a user group. So what I can do is hadoop. So I can actually give Impala permission fs hyphen, I can set a ACLs hyphen u hdfs hadoop fs hyphen set facl. Set facl is actually like we can give other permissions to particular users or groups using this acls, access control list. So hyphen m. So this will be, I believe this commands you practiced in like the hadoop sessions section. So set facl, you can go to hadoop command guide and see actually the usage of set facl. So set facl hyphen modify, hyphen m means modify the, add extra privileges, modify the existing privileges. I am adding a group privilege. I am adding group hive read write execute. I am giving the group hive read write execute to the path user slash ec2 hyphen user. So this means like the user hive, the group hive, all the members in the group hive will get read write execute to everything. So I just forgot to put recursive hyphen r. So now all the members of group hive will get read write execute to all the files inside this, or files and folders inside slash user slash ec2 user. So now we will try the Impala shell. Now we'll execute the other query. So this table got created, see. Sorry, we have to choose the database testing. Clear is not a command actually, so that is the reason. So tables, so show tables will list all the tables, show databases will list all the databases. So now we created it, data. So we created that table in a different database. So what we can do is we'll create the table in this database, in the testing database. Yeah, so it got this sample table one got created in the new database. Previously we created the sample table one in a different database. So this is the location where this table is pointed to. So I have a sample file. So this, the schema of this table is like, first is an integer value like integer, second is a boolean, third is a double, fourth is a timestamp. So I have a sample dataset with me. So this is my sample dataset. So first is an integer, second is a boolean, third is a double value, fourth is a timestamp. So I am going to put this to HDFS, set of hadoop fs hyphen put. First I will create put this sample.csv to the location there where we created the table. Sample.csv to this table directory. So again permission issues there because this was created by Impala. Now it will get uploaded. I just give record permission there. Now it will, because this table was created by Impala, so it will be owned by the Impala user. So when I try to use EC2 user, so it will not get uploaded because it is not having write access. See, it's not having others. No, it doesn't have write access. So if I do star from sample table, so it gave me this result. Select star from sample table, gave me this result. It gave me this result properly. So select call 3 from sample table 1. It's giving me results very quickly. So this is the power of Impala. It gives the value. Like similar to this, you can execute hive queries, like any hive queries in Impala. Like most of the, like the one of the drawbacks with Impala is like Impala will not support Serdes and all. So Serdes support is still not there in Impala. And so like other than that, like majority of the hive queries, most of the hive queries can be executed in Impala. So then similarly we'll create an external table right now. So examples will point to the location sample 2. First we will create the directory, then we will load the data. The sample1.csv to this directory. So it's again same schema only. The only difference is it's an external table. First one is a manager table. Sample 2. So it got created. Show tables. From sample 2. So we will get the output very fast. So we got the output. Second time in query we will get the output very fast. It's quick. So then if you want to find the details of a table, describe table. So describe, then the table name will give you the details of the table. If you want more details, then describe formatted table name. Then describe formatted table name will give you everything. So second table is an external table. So here you can see describe formatted sample 2. It is giving the complete, the column name, data type, comment. So first id is actually an integer column type, boolean, double, timestamp, then database is testing, and who created the table. I, like EC2 user, as the Linux user who created the table. Then this is actually the create time. Then this is actually the HDFS location, and table type is actually external table. Then like the input served library. So all these things actually it is mentioned here. So that is describe. Then invalidate metadata again. So we have actually invalidate metadata command. So invalidate metadata will like refresh the loaded metadata, like in memory copy of metadata. Then we have insert commands. If you want like create table test to as select star from sample underscore, what is the table name, table 2, sample underscore table 2. So it inserted it created a table test2 as, so this is the query that executed, create table 2 as select star from sample underscore table 2. So it created a table called test2, and it actually took the output of data from sample table 2, and it returned to so the test2. So I got a table and it happened in like very quickly, 0.47 seconds. So similarly, I'll create another table, create table test 3, select id from sample table 2. See, inserted 5 rows. It happened very quickly. Select star from test 3. These are some of the examples. Then describe test 3. It's a single id alone, and it is a managed table. So because we created actually managed table, we didn't like we just specified like create table only, so we didn't put external table, so it's a managed table. So these are actually this is actually the basic overview of Impala. So we can like practice any kind of queries in Impala. So queries I'll be I'll be putting more queries along with the assignments. So this is the way actually to interact with Impala. And like one more thing, I discussed previously, like you can connect to any node, any like if in a multi-node Hadoop cluster. So there will be Impala servers will be running in a number of machines. So it is not necessary that actually you have to connect to Impala of the same node. You can connect to any of the Impala nodes. So you can connect to any Impala server using the command impala shell -i, then the Impala server hostname. So here my hostname is master. I put master, so it got connected to master. If I have another machine, it will get connected to that machine. So that is the procedure. Then another topic regarding Impala is like, so we discussed till here. So we didn't so we discussed the basic querying of Impala, querying through Impala only. So remaining advanced queries and all I will send you along with the assignments. So then authentication and authorization with Impala. So in a production cluster, so we need our like all the requests, all the users to be properly authenticated. So Impala supports Kerberos. So we can actually enable for authentication. So from a developer's perspective, this is actually not that much required, but I'm just actually explaining it here, and this is actually an advanced topic also. So when you see in production clusters, so Impala will be like the authentication. Impala supports authentication using Kerberos. So Impala supports Kerberos authentication. So when you log in here also, you can see to the Impala shell. So Impala shell. So here you can see actually somewhere it's like starting Impala shell without Kerberos authentication. So here this is actually a non-Kerberized cluster. If it is a Kerberized cluster, it will start with Kerberos authentication only. So then it will connect to the Impala server only if we have a valid Kerberos ticket. So if you don't have, if an unauthorized user tries to log into Impala shell, it will fail. So this is a non-Kerberized cluster. That is the reason I am able to connect without any Kerberos ticket. So if it is a Kerberized cluster, every user needs valid ticket. So Impala supports like Kerberos, like that topic anyway, it's not part of this section, but I'm just telling actually Impala supports Kerberos authentication. And another thing actually is authorization session. So authentication means once a user is authenticated, suppose like I authenticated, like using Kerberos, I authenticated user 1, user 2, user 3, user 4. 4 users I authenticated. Now I am saying like 4 users are eligible for accessing Impala. But again, the problem is actually in our Impala we have databases, multiple databases, multiple tables, like we have we can have n number of databases and n number of tables. So if you are simply allowing all these users to access all these databases and all these tables with all the privileges, they can do anything in this databases and tables. So that is again actually a big problem, because suppose user one created a table called database called db1, user 2 created db2. So when user 3 he checked, he can see db1 and db2. What he did drop database db1, he deleted the database. So who lost the database? User 1 lost the database. So if you are giving open access to all the authenticated users, similarly like user 4 dropped tables inside db2, dropped the tables inside db2. Again, this is another problem. So if we are giving open access to all the authenticated users, it will be a big problem. So we need proper authorization. So like a newly developed Apache project called Sentry. So Sentry, actually I'm just telling the name, actually just like mentioning the name. You can read about Sentry in detail, but Sentry is a different topic actually. So Sentry allows granular authorization to tables, databases, partitions, etc. in Hive and Impala. So Impala supports Sentry. So once you enable Sentry, using Sentry we can block or we can restrict the privilege of a user to, like we can have select privilege, we can have insert privilege, we can have like all privilege, we can have all privilege means select and insert. So we can have no privilege, we can have an admin user. So like that we can have actually multiple privileges. We can have select access, we can have insert access, we can have all access to a particular table, a particular database, a particular like location. So like that we can actually segregate, like we can separate the privileges, we can define the privileges of for a particular user. So that like if we define here using authorization, if we define like user 1 has only read access to db1, user 2 has only read access to db2, then user 2 can't do anything inside this, like can't insert any data inside db2, he can only read db2. So similarly user 1, he can only read db2, he can't delete or insert anything in db2. So like that we can actually define the privileges or permissions actually. So with authentication and authorization, proper authentication and authorization, anyway Impala supports authentication and authorization. So Impala supports the authentication using Kerberos and authorization using Sentry. So using this Impala is right now a stable product in industry. So a lot of production projects are actually running in Impala. So with this authentication and authorization, Impala is actually an enterprise grade product. So that is actually that is a very brief explanation about authentication and authorization support of Impala. So the next topic that we have to cover is the managing resources. So managing resources means, suppose I'm just taking a new slide. Save mine. Okay, suppose if you have a big cluster, this is actually your 100% resources of a cluster. So you have a Hadoop cluster, so 100% with 100% resources. So you have yarn here. So this is a Hadoop cluster, you have a yarn here. Impala. So we can actually run Impala in two ways. One is actually managed through yarn, another is unmanaged. So I'll discuss that. So right now this is actually unmanaged. So this is actually a cluster, 100% resources. Some resources it is used by yarn, and some resources it is used by Impala. So like both of them don't know actually how much. Proper resource management will not happen. Resource management will not happen actually until and unless there is some rules defined. So if both are actually trying to share the same resources without any control, what happens is at some point yarn may take up like yarn may take up like, assume like the clusters are free, so yarn take up 60% of the resource. Yarn may actually occupy this much resource. It will try to occupy this much resource. It will try to occupy this much resource, and Impala when it checks, so it also assumes that actually the cluster is free, so it will try to take up the remaining resource. So it will try to take something like this, so the overlap will happen finally. So again Impala will take up actually the remaining. So suppose this is yarn, and Impala will assume actually the cluster is free. So for a bigger query, what Impala did was Impala needs some 50% resource. So yarn took 60-70% of the resource. Impala tried to take acquire 60% of the resource. If in this case the resource overlapping will happen, so out of the 100%, the requirement will become like 100, like 60 plus 70, it will be like more than 100%. And like yarn jobs fails, Impala job also fails. So there should be some unified mechanism so that will allocate the resources properly. So that will allocate the resources properly. So we have actually two mechanisms. So one is through yarn through Impala managed through yarn. So one way is Impala managed through yarn. This is actually accomplished, like this is achieved using llama, so low latency application master. So another is Impala admission control. So first one is through through managing Impala using yarn. Another is actually Impala admission control, through Impala admission control. So Cloudera developed actually one facility to limit the resource utilization of Impala manage the resources inside the cluster using Impala admission control. So if you have Cloudera manager, if you are using Cloudera enterprise, so you can avail this feature. You can actually see this Impala admission control in the web UI, like Cloudera manager UI, dynamic like Cloudera manager UI. So there the basic funda is actually like you will define like 30% of the cluster example. It's an example. Resources to QA, 20% to QB, and like 50% to QC, 50% of resources to QC. So similarly, like we created multiple queues. So it's just like another way of scheduling. So we created multiple queues. So 20% of the cluster resources to QA, 30% of the 30% to QA, 20% to QB, 50% to QC. So here actually it is well defined, and in QA itself, this is actually I'm telling about admission control, and QA itself we defined like MapReduce this much resources, like 30% of the resource means like they can take it can take this much resources in MapReduce, this much resources in Impala. So we will actually define the numbers, like we will define the numbers for Impala as well as the yarn. So that is actually in case of admission control, but admission control actually it is available only through this feature is actually available only through Cloudera manager, like this Cloudera Impala. So that a very good UI is available through Cloudera manager, so you can check that. So this is anyway actually this is an administration part, so I just mentioned here, so you don't have to worry about this thing much. Then another is actually Llama. So Llama is actually low latency application master. So Llama is low latency application master. So we discussed here, like if Impala and Yarn independently access the Hadoop same cluster, so in that case the resource requirement may overlap, and Impala jobs, because of the overutilization of the Impala jobs, the Yarn jobs may get killed, and similarly because of the overutilization of memory utilization of the Yarn jobs, and Impala don't know what is happening with Yarn, so it will kill Impala queries. So that things may happen. So in the initial, in the introduction part, I mentioned Yarn is actually a general purpose framework. It's a general purpose resource management framework. So Yarn can be used for submitting any application to the Hadoop cluster. It acts as a generic resource management. It is actually Yarn actually provides a generic resource management. So this is actually basic. It's very helpful for shared clusters. So if we submit Impala queries through Yarn means not MapReduce, but if we get the resource allocation, through Yarn, then it will be we have actually one person knowing what resources are allocated to Impala, what resources are allocated to MapReduce. So all those things Yarn will know. So that is achieved using Llama. So Llama is low latency application master. So it will launch, actually low latency means it will quickly launch. Impala needs, when a query executes, Impala needs the resources very quickly. It needs everything at a single time itself. For a MapReduce job, what happens is the allocation will happen step by step, because it is actually a batch process. So depending upon the requirement, resource manager allocates the resources bit by bit. It will be allocating actually small pieces, it will be allocating in an incremental way. But in case of Impala, the requirement is it needs everything in a single shot, and it needs if it needs 50 GB memory, it needs the 50 GB memory in a single shot. So what happens with the Llama is Llama will it will launch the application masters very quickly, and it will capture the required resources from the cluster through Yarn. So Yarn allocates the memory if it is available. If it is not available, Yarn will not allocate actually. So like that we will have actually a proper resource management in the Hadoop cluster. So in that way the resource management will be properly established. So we have actually two ways to manage resources. One is through Llama and another is through Impala admission control. So admission control, it is again both are actually one. The thing is, Llama is open source, it is free, and Impala admission control, it is from Cloudera. So there are differences are actually Llama is open source, so Impala admission control actually this is actually from Cloudera. This is actually not open source, this feature. So these are the difference actually. Both are actually both are providing actually the same feature, almost same feature, but it is actually from one is actually open source and free, another is actually it is actually from a company. That is the difference. So with this actually we covered almost all topics. So I have actually a sample slide, so we will go through that slide, then we will discuss actually one by one. We'll just have a refreshing session for 5 minutes. So like, what is Impala? It's like a relational query engine we already discussed. It's open source and free. Then it works with massive parallel processing technology. It works with MPP, so it's like MPP. It works with the technology of MPP. Then it executes SQL queries. Then data is append only, and there is no update or delete statements. As of now there is no update or delete statements, but in future it may come, because like hive also, like the delete statements are, like right now in the recent versions of hive it's available. So like this will also come in Impala soon, I believe. So because HDFS, it totally depends on the like properties of HDFS is actually append only. So that is the reason actually, like here also, like Impala is also again append only. And this is developed by Cloudera. Impala is actually developed by Cloudera. It's an open source project. It is actually free to use. Then this is actually the base architecture diagram that we discussed about Impala. So we have Hive Metastore and we have Impala. It, like, people can access through ODBC, and Hue we can access through Impala shell, and like underlying layer is actually the HDFS. We can have HBase also. Impala can query from HBase also. So it can, like, it can create actually tables on top of HBase tables. You can query from that. So that feature is also available. Then next is, does Impala uses MapReduce? So we discussed, like, Impala is not using MapReduce. It is like, it has its own processing engine called like it has an MPP, massive parallel processing framework. So it is not using MapReduce. It uses actually the HDFS, but it uses actually its own processing engine. Impala gives near real-time results, but it depends actually. Sometimes actually the query may last for an hour also. It depends. It totally depends on the type of the query and size of the data. Then relation between Impala and Hive. So Impala uses Hive Metastore for the metadata store that we discussed and that we have seen also, and it's not using MapReduce. Then we can query actually the tables created in Hive using Impala, but all the queries are not supported because some services and all, it's not supported in Impala. So Impala, like most of the tables actually we can query, but some tables, some types are actually not supported in Impala. So like suppose some services and all, actually it is not supported in Impala. Then Impala and Hive shares the same metadata store. But yeah, then like another use case actually, what I'm telling is, like, Impala needs, I discussed, like Impala needs more memory. So if your requirement, like if you don't want the queries very fast, like if you don't want the output of queries very fast, you can use Hive. Then the end results anyway, it will be like the final queries, the publish layer tables. Those tables will be actually, like, the size of the table will be less. So those data we can query using Impala and perform the visualization using some visualization tools. So those will be like very impressive, because if you get a near real time results from like tables that are actually the like final publish layer tables of some large data, after some large data processing, it will be very impressive. So Impala can be used for like querying the like end results. So using some visualization tools and all, so it will be very impressive. Then next is, does Impala need a separate cluster? This also we discussed. Impala runs along with Hadoop cluster, so it will use HDFS. So it has, like, in all the node we have actually Impala server daemon running, and there will be actually one catalog server and one state store service. So these services will be running in one node. In all the other data nodes, Impala server will be running. Then which distribution of Hadoop is compatible with Impala? Impala is developed by Cloudera. So all the, like, from CDH4 onwards, like all the Cloudera Hadoop versions are compatible with Impala. But if you compare, like if you talk about the other distributions like Apache, the plain vanilla Apache or Hortonworks, like we can actually make Impala work with the other distributions also. We just have to compile Impala source code with the jars, and we just have to install Impala. That is the thing. So, and Amazon is providing Amazon EMR, Elastic MapReduce. So it has actually Impala also. They are giving Impala also, so we don't have to do anything else. So we can simply install Impala using one click in Amazon Elastic MapReduce. It is a service. So you can check that also. If you want ready-made cluster in few minutes of any number of nodes, you can actually use Amazon Elastic MapReduce. Then which language is used for developing Impala? So Impala, if you talk about Impala, like Impala shell, like the core part of Impala, is written in C++, and core part means actually the services: Impala server, Impala D service, then state store service, then catalog service. All these services are actually written in C++, the core part. Then actually the the front end part means core part we can call it as backend. The front end part actually it is written in it is written in Java, and the Impala shell and all it is written in Python. Impala shell is actually written in Python. Then daemons associated with Impala. So Impala, like, it's totally written in three languages: Java, Python, and CPP. So C++ is actually the core part of Impala. Then daemons associated with Impala. So we have state store, Impala server, and Impala catalog server. So we have three services associated with Impala. Impala server will be running on all the nodes. Impala catalog server and state store will be running on one node. So Impala server, as known as, also known as Impala D daemon. So it is actually, this is actually the this is the place where the actual query execution happens. So it has actually basically two sub services. One is actually Impala service. So this is actually used for executing query. Then all the JDBC, ODBC connection, everything happens here actually. So this is actually basically for the query execution. So Impala, the other service is actually Impala internal service. So this is actually used for working, this will actually coordinates with the other Impala server nodes, and this will actually this is actually very required for the query execution, because the coordinates means Impala is again actually a distributed processing framework. So Impala needs to communicate the I discussed, the query will be submitted to a machine. So that machine acts as the master node. So master, we will call it as coordinator, and it will divide the query into small pieces, and it will give the fragments of queries to other nodes. So other node act as the executor. So each node needs to communicate each other. So these communications actually it happens through the Impala internal service. So all these internal communication happens through Impala internal service. So does Impala has a master slave architecture? So when we see the picture, it doesn't have a master slave architecture, but it actually there is no single point of failure. There is no single master in case of Impala. Impala, any node can become a master. So we discussed all these things previously. So any node can become a master. Wherever we submit query, that will be the master of that query, and remaining will be the executor. So that is the case. So and all the queries are actually processed in a parallel distributed way. So that makes Impala actually horizontally scalable. So roles of an Impala server. So Impala server, it can act as actually a query executor as well as a coordinator. So if we submit a query to an Impala server, that node acts as the coordinator. So if it gets actually a query fragment from some of other Impala node, it will act as the query fragment executor. Then Impala state stored, we discussed the detail, it is actually responsible for managing the synchronization between the Impala servers. It is just like actually Zookeeper. It's not Zookeeper, but it is actually it's doing actually a role something similar to Zookeeper. It actually maintains the synchronization between the Impala servers. So this happens through state stored. Then we discussed this also, what are the main topics of state store: Impala request, queue topic, Impala membership topic, Impala catalog topic. This we discussed already. Then Impala catalog service, again we discussed this topic. So this is actually like it uh, it actually relays, this actually relays the metadata changes from Impala SQL statements. So whatever happens through Impala, it distribute across all the nodes. So because if any metadata changes happens through Impala, it distributes like across all the nodes actually, and this is actually achieved using state store. So state store and actually catalog D are actually the catalog service distributes the these details to all the nodes through state store daemon. So this is actually another, like while installing Hadoop the Hadoop cluster, I mentioned short circuit read. So we have to enable short circuit read in HDFS for faster performance in Impala, because short circuit read means when you, like in normal Hadoop cluster, when you read a file from HDFS, first actually the request goes to name node, then actually the request will be routed to data node. So data node, what it will do is it will read the blocks, then it will stream the blocks. First the data node, there is actually a process called the data node. That process will read the data blocks, and after that it will stream that data blocks to the client through a TCP socket. It will actually send the data blocks through TCP socket. So for every read there will be actually a data node process in between the client and the data blocks. So in case of like Impala actually is we need actually output very fast. So if we actually put the data node process in between the data block and the client, every operation needs the data node intermediate, it needs actually the intermediate services data node. So to just bypass this file streaming through data node, first the data node reading, it will be first reading through first the file will be read by data node, and it will be sent through a TCP socket to the client. So this is actually first it will be read by data node, again it will be sent to the client through TCP socket. So this is a two-step process. Instead of that, if we can read the data blocks directly from the client, it will be faster. So that is actually short circuit. Short circuit means, I'll draw it here. So short circuit means you have file system here, you have data blocks here, so you have a process called data node, and a client requested for a data block. What will happen? So it goes here, then it goes here. So first data node will read, then it will send to client. But if we can read directly like this, it will be faster because we can avoid the intermediate data node. This is called short circuit. So this has to be enabled. So this client, in case of Impala, this client will be the Impala server. So Impala server will read actually the data blocks directly from the storage. So it actually bypasses the data node. So that is what we call a short circuit. It is required actually. So it needs to be enabled in the Hadoop cluster so that it boosts the performance. Then next thing is query execution steps. So we discuss first the query. It will be an SQL query. So the query will be parsed first. Then after the parsing, it will actually just check as I discussed, every table it will be having schema as well as data. So it will actually first match the metadata, objects to metadata. So it will actually check the metadata, then it will actually plan, it will create an execution, physical execution plan for the query. So how to execute, like how much memory is required for that query, all these execution plans will happen. So it will plan first, and based on that actually it will plan like per node memory requirement. The entire query requires this much memory, and per node this requires actually this much memory. All those plans will happen. Then it will actually divide the query into small fragments, and it will distribute the fragments to multiple nodes. So this things will be actually happening in the coordinator node, and it will distribute the fragments to the nodes. It will actually, this happens in the coordinator node, so it will actually distribute the fragments to the nodes, and finally the executors will execute the plan fragments. The intermediate results actually, like executors actually also communicates between each other. So the intermediate data results, like all those things actually it can communicate with each other. Finally actually the query results will be sent back, results will be actually sent back to the coordinator, and coordinator will send the results to the client. It will actually reply the client like where we submitted the query with the results. So that is actually what happens with Impala. So this is actually the query execution steps. This is very simple, like query parsing, matching objects to metadata, then query planning the query, like then divide the plan into fragment of 4 nodes. Like it is actually processed in distributed nodes. So it will actually divide the query plan into fragments, then it will distribute the fragments to the individual nodes. It will execute it, it will send back the results. Then user defined functions. So Impala actually, like I told you, like the core part is actually written in C++, so C and CPP. So we can actually write Impala UDF and UDAF using C or CPP, and using Java also it supports too. So Impala access, how to access Impala, it can be accessed through Hive or through CLI. It can be accessed through Hue, not Hive. It can be accessed through Hue or Impala shell, or through any like programs like Python or Java programs using JDBC or ODBC, or through any extra applications, third-party applications like Excel, Spotfire, Tableau, etc. Using ODBC, JDBC connectors, all these things will happen. It's possible. So limitations of Impala, like Serdes and all, actually it's not supported. Actually that much support is not available in Impala currently. Then buckets, samples, transforms, arrays, structs, like complex data types, lot of things are actually not supported in Impala. Impala is actually still getting, like the features are getting added, but it has actually like some limitations compared to Hive. So which one is better or best, Impala or Hive? So this question is actually like something like, this is a trade-off. So we have to decide based on our use case. So if our requirement is like execute very huge queries and we are not concerned about our time, then like if it is very huge, and we can like surely say like if it executes in Impala, it needs lot more memory, lot more hardware, then Hive will be the best choice for if you don't have time as actually a problem, constraint. But if you have time as a constraint, and if you are actually like having good hardware, and if your data size is also like fine, then Impala will perform well also. So it's like a trade-off. It totally depends on your use case, size of data, time that required for processing queries, all those things. So then these are actually some useful references. All these are actually like Cloudera slides. So these are actually very useful references you can use. Then how to practice Impala, so that thing actually I already discussed in the video. Then practicing Impala in cloud servers. So I like the like whatever I discussed, it happened, like I did it using like a cluster created in AWS EC2, Amazon Elastic Cloud Compute. So you can also practice something similar to that. So you can also practice something similar to that. So that is actually, like, this is actually much about like whatever we discussed till now. It's actually more about theoretical part of Impala. So we can actually, like, I'll actually put the assignments, actually, like, it will be attached along with this content, so you can practice the remaining assignments. Assignments. Okay. Okay, thank you very much.